So last week, I should maybe jump to last week. We saw categories, which were a generalization of monoids, where everything is just type aligned. And then we saw some examples. So the most obvious one was to have some kind of function as your notion of morphism, and then you have the usual identity, the usual composition, and everything is just well behaved. But we saw that you could have more interesting setup. So you could have the discrete category where the morphisms are boring. You could have, well, they're boring. They do contain some information, but you could have any kind of poset, basically, gives rise to a category.
Doesn't have to be a poset, just has to be a preorder. But
right.
You don't need anti-symmetry.
Right.
You do need irrelevance. That's the crucial thing.
Yeah.
But isn't that once you know that a morphism exists, you don't need to know any more about it. It's not a question of which one is it.
Yes, and then we saw the Kleisli category of a monad. So this idea that categories are describing what it means to be closed under composition, and Kleisli tells us that effectful computations where the effect is modeled by a monad are closed under composition. And the rules, like the constraints you have on bind and return, are exactly what you need to be able to prove that it forms a category. So when we introduced these constraints back in 3.16, it was not just by chance. It was to ensure that everything was well behaved.
Did anyone, probably Bob, ever show you anything about for logic for programs, for like precondition, postcondition logic for reasoning about sequential programs?
I know he does it like this nowadays in 208.
Whether he did it when you were in second year is another matter.
Yes.
But there's a kind of general notion in imperative programming languages that, you know, the semicolon languages, right? You know, the ones where you put a semicolon between do this and do that, and it means do this, then do that. You can also, there's a program, it's less useful, it doesn't often get actually formally called skip, but that's its familiar name, that kind of the empty curly braces, or whatever it is that does nothing, right? And what we're saying when we say a monad has a Kleisli category is that return is the thing that does nothing, and that composition behaves like a semicolon. It works because whatever stuff the monad lets you do, you can do it in, there's a way of doing nothing, and there's a way of doing it in sequence. That's all that's going on. It's perfectly, you know, all we're saying is empty curly braces and semicolon do exactly what you expect. Nothing else is happening here, right?
Yeah, so then we saw that from any monoid, we could derive a category. So this was a way of illustrating what we meant when we said that categories are just a fancy monoids,
yes.
In that if your notion of being fancy is just the unit type,
yes.
so there's no information whatsoever stored in it, then you get back a monoid, essentially. It goes both ways, although we only showed it in this one direction. But
yeah, yes. So yeah, monoid category, one object category.
Yes. And then we saw another spin on this, which is to say that now we can consider, instead of a single monoid, all of the monoids that exist. And the notion of morphism or transformations between them is the structure preserving map. So the monoid homomorphisms. And then we saw that we could define an identity, which the action on the object, on the underlying values, is literally the identity, and that is well behaved. And then we could define a notion of composition, which again, the the action on the underlying values is the composition of the actions, but then we need to rely on the fact that we are indeed structure preserving to be able to prove that then the composition itself is well behaved. So that was pretty fun. And then we saw the generalization of crush that we saw on monoids, so or folds in CS316, which is taking a list of values in a monoid and reducing it to just a single value by crushing all of them together. And we said, well, this time we have type information, so we cannot just have a list anymore, but we have something that looks an awful lot like a list. If you forget about all of the indices, you just have an R and more R's, and then you can have no R whatsoever if you want. So that's what is the definition of path. And we saw that it's the reflexive transitive closure of a relation, if we want to get technical. What this means is that for an arbitrary relation, no assumption whatsoever on it, we can prove that the path over R's are reflexive and transitive. And then we saw that you can define crush, and it is well behaved in that it sends the identity for path, so path from S to the identity in the underlying category. And then if you have two paths, if you combine them first using transitivity, which is to say composition for the paths, so from S to M to T, it's the same as crushing both paths in parallel and then combining them with composition.
Yes. Did we actually then build the path category?
No, we didn't, and we didn't prove that this defined the functor, basically. Yeah, right. So this is today's goal. So if I go back to week 10, we are back in here, and we can say, okay, well, let's define the path category then.
You'll need some underlying.
So if we have a set of points of type A and a relation at level L, so we saw that paths, because they were storing the middle points when we had a first step and then a further step, it needed to be at least of size A because we're containing values of size A. And then we're storing proofs of size L, so it needs to also be at least of size L. And then, okay, I gave it different names here. And so we took the lowest upper bounds of these two. Okay, so the objects here are going to be, well, maybe I should call it C for uniformity. They're going to be the points themselves, right? Because the paths are always between two values of type A. But then the morphisms are going to be paths, so they will be big, or rather potentially bigger than, and of course I don't have the right import around using lob typed LUB. And now we can define it.
Yes, I think your locally opening category is good move.
Yes. So as I said, the objects are just A's, and the morphisms will be paths using the relation that we're given. And so then we said we have an identity. Oh, let me scroll in. And the identity is saying, well, if I start from an object, I can always stay on that object. And this is exactly what the reflexive proof was giving us. And then this is, again, exactly what transitivity gave us. So we have transitive. Oops. And then we need to prove some results, which we don't have around, I think. So we'll need to.
But, you know, they're around. Yeah, I mean, it's hilarious, right?
Yes.
Just as, whilst these types may not be familiar, these programs are extremely familiar.
So they're just fancier versions of programs we know and love. And so the proofs, there's no need to even think. Oh, I didn't bring the constructors along. Up. Let's get rid of these qualified names. So as always, when we want to prove associativity of a pen, we proceed by induction on the first one. In the base case, it's gone because it's empty. So we are left with a compound expression equal to itself. And then in the step case, things compute enough that the first term pops out. So we can use congruence to ignore it or move past it. And then we're under the cons, and now we are just dealing with the induction hypothesis. And here I'm hoping that the termination checker will be clever enough to see this. Is okay. Yes. Well, I mean, technically we're defining a record, and here we're projecting out the records. But it's
generally good at this much. Yeah.
It's not too bad. It's able to see through the layers of abstractions. Usually, as soon as you introduce some kind of interaction, you're in trouble. But records are quite well behaved.
I want to bring M into scope because you need to do, well, okay, one of them will be fine.
Yeah, so this one is fine, right? It's the same as append and nil being a neutral for append on the left, but it's true by computation. So that's REFL. And then this one, well, it's again the same story, right? We have M appends nil, and to prove that, we need to proceed by induction on M. So I'll bring M in, and then I'll k-split on M. Ooh. We have many things that are hidden, so I need to name it, and we might as well give it good names. Okay. And then in this case, same as ever. This thing pops out. Okay. So I think if it were an auxiliary definition, auto would be able to find that induction hypothesis call, but here it's just slightly too complicated, so I need to write it down by hand. Okay, so now we have a category, and if you scroll back up, you can see that we have no assumptions whatsoever for R, right? So in a sense, this is a free category we're building for any relation R, just by, I mean, making the morphisms the paths is exactly what we need to be able to absorb that appending aspect, right? That composition aspect. I mean, that transitivity, essentially. So,
yeah,
I guess
might be worth trying to look at this word free.
Yeah.
Right. So the point here is that we are saying somebody gives us any old R. And we're saying, what do we have to do? What's the least thing we have to do to make those things the morphisms of a category? And that's to say, we have to throw in identity and composition and make it associative. And we make it associative by saying, we're always going to nest on the right. Well, that's what the cons is giving us. So the thing that is the sort of least you can do to impose the structure, even if you didn't have it in the first place, is often called the free such thing. So this is construction for the free category. Sometimes you might hear us talk about lists being the free monoid. So that's to say, you know, you've got a set of any old stuff. It's not automatically a monoid, but strings of them, lists of them can't help being a monoid. Freeness comes with a particular property, which is to say that all the structure preserving maps out of the free thing are determined by what you do with one element. So that's to say, it's the thing we had earlier, right? Remember when we say, how do you make a monoid homomorphism out of lists? So from lists into some other monoid, you just say how to map each element to something in the monoid, and then after that, there's no choice. So the same, so the fact that you know you're going to get all of those homomorphisms that way is what makes knowing it's not just any old category, it's the free one, really useful.
Yeah, so another way to look at it, right, is to see any relation as a graph. So you have your set of points, right? And then your relation is telling you what edges you have between your points. And what it means to have a category for a given relation is a bunch of constraints on the structure of the graph. So the graph should have always an edge from each point to itself. This is all the identities. And the graph should also have, whenever there's a path between any 2 points, you should also have an edge between them. Because by composition, you can crush that path to a single one, right? And so here what this is saying is that we are happy to take any graph whatsoever as an input, and then we're going to do some sort of completion, which will add all of the missing edges in the relation. So we're saying this is adding all the identities, right? Because you have the empty path. And this is also adding all of the composites because you're literally taking the path as your underlying notion. So you're starting from your small thing and then you're throwing in anything that's needed to make all of the proofs go through.
So that's dead right. The category is saying the paths have to give you edges. And the free category is saying, well, what if we just made the path the edges? If we just said the edges were the paths, then we're done, right?
But that's a common pattern in computer science, right? You have something that's not quite what you want, and then you have a completion step that will just throw in extra things so that now it has the right properties
only just
for
enough.
your thing. Okay. And then what I wanted to do, but maybe you wanted to do freeness instead?
No? I mean, we should do functors.
Oh yeah, functors. I was already going to the next thing. Right. So what does it mean to be a functor? Well, we said it's a bit like being a monoid homomorphism, but for categories instead. So it's, again, this idea of structure preserving maps. So let's do
there are choices.
Just that.
But we're going to make the obvious choices, I hope.
No, 1, no, 2. Well, I don't know what the obvious choices are, but maybe I can.
Everything goes forwards.
Oh, I see. Yeah. Well, it's all equivalent anyways, right? Oop. Let's call it source and target. And so we're saying, should I do this?
Yeah.
And it's going to be, so we have C1. Maybe, we'll see, whatever. So we have the home fun. So what we're going to do, okay, I need to give myself names for these source and targets. Module T is the category T. Right.
Home fun. I mean, we're going to say there's going to be an action on object.
Well, I think that's what we called it for monoids, right? I was just, maybe I should bring that definition back.
Right. But there was only one function.
Yeah.
So we want kind of,
Yeah, but
now we've got two components.
baby steps, right?
Yeah.
So if we try to write what it means to have a function on the morphisms, then it's not really clear what should go in there, right? Because if we look at the morphisms in the source and the morphisms in the target, well, these are objects in S, both of these, and these are objects in T. So we could universally quantify over everything, but then it's kind of strange. Like, do we really want a function that goes like cross paths, and then how we're going to state that identities are preserved if our input can take us that just doesn't quite work. So what we do instead, and we can think of it actually as a structure preserving morphism on graphs, right?
Right.
So we start with a bunch of nodes in both categories. And first of all, we need to relate the nodes from one to the other. So we're going to need a transformation from source node to target nodes. And then what we want to do is preserve the edges, right? If we're thinking about structure preserving. So whenever there's an edge between two source nodes, there should be an edge between their image in the target.
Right. And it's terribly, one of these things where it sounds more complicated than it is, right? All we're saying is that, for example, a map of the ScotRail network would be perfectly useless if the line that joins Glasgow Central to Paisley Gilmore Street on the map corresponded to the line from Glasgow Queen Street to Falkirk in real life. Then it would not be a useful map, right? Point is that the lines that join the dots on the map have to join up the places the dots talk about, you know, in real life. Yes.
So our first decision here is to decide what we do with objects. And then once we know what we do with objects, well, we want to say that every edge has an image. So we can give ourselves a source in target, but I'll write it explicitly actually in S. And then for an edge in S between the source and target, we want an edge in T between the images of the source and the target.
Yeah.
By the transformation we picked.
When I say there are choices, all I mean is that you could work it the other way around, right? This arrow could go backwards. And we could quantify over objects in T and say where those things come from. So there are choices about how to cook this, and you get subtly different things depending on which you make. But everything goes forwards is your basic rock and roll.
Yeah. All right. So that's what these things has turned into, right? Here for monoids, if you remember when we presented them as a category, we said the set of objects is just the unitype. There's a single object, and then the morphisms are describing the various ways in which you can multiply in the monoids. And here, we just generalize this to saying, well, we actually have an interesting function between these things, and then we go from the source value to the other one. And what we're saying is that that function should send identities to identities. So let's just write that then. Properties, so functions. Oh, shoot. Can I not have both on the screen? So we call, well, I suppose it's going to be identity then.
Yeah.
And it's taking the home fun of some identity. Okay, but that's bad. And it should give us in S and an identity in T. But yeah, for any object. Oh. Okay. Toot, toot, toot. And then we have composition. So, and then, just to say that if we have a F and F is a morphism in S, and G is a morphism in S, and they're taking us from S to T via M. Then, and that's the expected thing, I hope. If you go from S to T first,
You'll need an S dot and then.
oh yeah, it's the same. And then, so if you go from S to T first, and then you push it through to the other category, it's the same as going from S to T in the other category and doing the composition with, no, it's the same as going from S to M in the other category and then composing it with going from M to T. G.
And
Do I need some parens maybe? Oh. Also the right name would be useful.
yeah.
Yeah, so it is just like this, right? You're moving the symbols through basically the transformation. And this is exactly what it means to be structure preserving. And then it should be possible to see that if you have three morphisms, right, we know we have associativity. Well, we know we have associativity in both actually because we have categories.
Yeah.
But we know that the transformations will basically preserve these morphisms also.
Yes.
Okay.
So what this means is that if you have some kind of join the dots diagram that asserts some equations hold about things composing together in one category, the functor will preserve the entire diagram across to the other category, not just the individual bits and pieces that make up the diagram. In other words, the map on your piece of paper, usefully corresponds to reality.
Right. And so then the last thing is to actually pick the level, and the trick there is to put the wrong one. Okay, this one is not even in scope, so it's even too wrong. Is it really only giving you, it used to give you the whole constraints. Okay, now you have to write everything. Okay, so it's not a trick anymore. Ugh. So you're slowly learning what the constraints are.
And it turns out everything's there.
Yeah. I should really implement
I'm slightly surprised
thing
by
that fills that in because it's...
Why is C2 there?
Because of these functions. Right.
Right, okay.
So we have functions over all the objects. Okay. And so then what we wanted to say is that crush is a functor.
Yes.
This is what we were saying at the end of last week.
I want to say that crush is a functor, but also that every functor out of path can be given as a crush.
Okay. So let's take this. Boop. All right. All right.
But now we know lots of things, right? This is because so many notions of structure fit in the world of categories. So each monoid gives you a category,
Oh no,
and
I
it
don't
turns
even know
out
this.
a functor from one category that happens to be a monoid to another category that also happens to be a monoid is exactly the thing we've been calling a monoid homomorphism. Right?
Oh. All right, so crush is a functor, but it's a functor, so it's taking in paths and then returning values or morphisms in the underlying category. So it's going to be a functor from the path category, which we can always get, right, for any sort of relation. And of course, here we're going to use the underlying morphisms. So if you have a path in a given category,
so what's going on here?
Into C itself.
What's going on here is that we're saying we're going to use the notion of morphism from this category, and we're going to forget that it's well behaved and just treat it as any old relation. So we are forgetting that we have categorical structure, and then path is saying, by brute force, I'm going to put the categorical structure back. So there's a connection between this kind of forget the structure and then do the least thing possible to get it back. These are very tightly connected ideas.
All right, so let's get there. So we said,
yes, we're identity on objects.
Oh yeah, because the objects in the path categories are exactly the elements the relation is talking about, and here the relation is morphism, so it's the objects in the original one. So we're not actually changing anything to the objects.
And then this thing here says, how do I get from paths to things? That's crush. You need
crush C. Yes. All right.
And then this is even true.
Ooh. Yeah, that's the horrible goal. And then if you normalize it, you get something.
And then this is the thing we called.
Yeah, so again, horrible goal.
Crush transitive.
But with a little bit of normalization, we see that this is what we've proven already. So. Oh, C. I need the category again. Yeah. I suppose here I could have used
crush reflexive, yeah, just by way of
just to hammer the point home, right? It is this idea that we are transporting the identity to the other identity. Okay, that's nice. Should I go the other way?
Yeah, let's see what happens. So somebody gives us a functor from path M to
right in here then.
Right, yes.
Oh, and you said you wanted a functor from
path M. So yeah, we need two categories. I mean, the number of categories that we need is 2.
Right, I don't actually need these to be explicit.
Yeah, because somebody's going to give us
C2, L2.
Somebody's going to give us a functor from path over S morphisms.
Oh yeah, okay.
You're going to want
we're getting
you can even do this.
Deep into syntax, yeah.
I didn't do that. Helpful. Right.
L2.
Yeah. Oh, have we got a module S already? I thought that was.
What?
Are we? I thought we were further out than that. Ah, fair. Good. Right.
Yeah, so you can throw in lead bindings in arbitrary telescopes because it's just useful. Do you
Right.
want to do it, maybe?
Well, let's see. Right. So the point is, my claim is that if somebody gives us a functor from S paths to T, we can actually cook up a functor from S itself to T.
Okay, that seems reasonable.
In fact, even
What should we call it?
or rather, we can cook up a function from S morphisms to T morphisms, because that's the thing we crush, yeah?
Yes.
Oh, we might actually, by the way, we might need a little more structure before we do this, but we'll get there. Right. Because crush is just a big concatenate, doesn't do any mapping. It's concat rather than concat map.
Yeah.
So before we do this, we need that any index respecting function. So if you give me if you've got a relation, right, so the point is, if you've got a relation on, if you've got a function that maps evidence for one relation to another, that gives you a functor from paths to paths. And then we are going to get exactly such a function from edges to edges, right? So the thing to keep in your head is, when do you have a category, when do you just have a relation?
Yeah, but here maybe we can just get the functor from S to T. What is that?
So, but
because then it's a composition.
No, so this is, we don't want a functor from S to T. We just want something on the underlying morphism.
Okay.
Right. I mean, what we're going to do, unsurprisingly, is that if someone gives us an edge, a single edge here, we're going to pack it up as a path of length 1 and send it over here. And that's a way of turning S edges into T edges in a connectivity respecting way. And then what happens is that we get, so yeah, this much we can.
Yeah, I'm not sure what to call it. That's my problem.
Yeah.
Of course.
Of course you need right. And that's the point, is that you've got your gadget. Yeah, because you've got, you know that because the objects of this path category are the same as the objects of S. Yes. Sorry, I'm being an idiot. I'm doing it wrong. My fault. T should be a category, but the thing on the left under path should just be any old relation.
Right, because otherwise we can define a functor from S to T from here.
Yeah,
But
So we should just have some
all right.
old thing, some old relation.
Oh,
So here you need A to A to set. And A is in set C.
oh.
Yes. Okay. And then you don't have that thing. And then that's path R. Right.
Mm-hmm.
Now it's not even a question of whether there's no choice. We're just going to talk about edges. Okay.
Mm-hmm.
And this is edge map or something. Right. And yeah. So that's an R thing that connects S and T.
It's an
The
home fun.
I know we can just say this is the singleton path. Okay. So that gives us something we can glue together. Right. So the next step on the journey is straightforwardly to say that if we have two relations like this,
Mm-hmm.
then that turns into a functor from between path categories.
Right. So.
Yeah, you do, and that should actually come first, morally.
Yeah. Okay.
So you still got C1, C2, and all of that stuff.
So we have two relations.
Yeah, you can leave those implicit, I think, because you're going to have a function.
From the path, yeah. Okay.
Yeah.
Dudes. R and
U. Oh yeah. Okay, fine. Yes. And then here we've got a for all ST. Yes, we've got one of them, and we've got.
so if we're able to turn
Yeah, you need
any edge in A into an edge in B over the transformed points.
So this is just a function that turns edges into edges. There's no promise about structure.
And then we have path map, which is, or map, let's call it map, which is a path RA functor to path RB.
Right, and the point is that this thing doesn't need to do anything about structure because we get all the structure from bigger path. Right, you know.
Or lowercase b. Because we're building the categories to be endpoints of the functor. Otherwise, it doesn't make sense. It's just the types. Okay. So this, I believe.
Do we want to locally open?
Yeah. Whoop.
With an equal sign.
Oh. All right.
So that's your F.
It's given to us.
That's your.
And here it's going to be list map, right? But for paths. So we need to define it by induction over the path. If we have the empty path, we're done. Okay, it's not clever enough to find this, which, I mean, fair enough, I suppose. And otherwise, we apply the transformation to the heads,
Should there be a space?
and we keep going with the tail. Yeah. Okay.
Yeah, I mean, it's kind of the point here is that
Oop.
things you're used to being true and things you're used to doing the proofs of turn out to not be plucked as things to want to prove from nowhere. They are the things that make structure happen.
Yeah, I mean, the type of this thing is actually quite interesting. Right? If you generalize again over F, you have for all F, you can take these paths along. Right? So it is a fancy map. Yep. Oop. Let's bring this back in.
Yeah, and then this.
And then, well, this is again map distributes over appends. So it's classic results. And we know it's stuck because the first thing is stuck. And then here we're just going to have the firsts. What? Oh, my bad. We've transformed it, of course. It's f of x, and then it's the recursive call. And then x is y's. So this is just automatic.
Yeah. So, so in particular, we now know that the edge map will give us a functor from path over R to path over morphisms in T.
Yeah.
And then crush will get us back to T.
Mm-hmm.
And those are two functors. And guess what? Would you be shocked if we told you that if you get two functors and you compose them, what comes out is a functor? Also that there's an identity functor, which does two kinds of nothing.
Yeah, it feels like something we should have done earlier, actually, but...
With 2 minutes of science left, we should do the identity functor.
Category
This one is at least a romp.
Up.
You need some...
Oh, lambda. Okay.
Phew.
Okay.
We did nothing, and guess what? Nothing happened.
Should just give up on this thing.
But you know what's coming.
CSLS. Boop, boop, boop. I should have been better organized because that would be more search and replace if I were declaring the levels and the thing also, but whatever. So if I can go from S to M and from M to T, then it won't surprise you that I should be able to go from, no, I suppose I can call it.
Yes.
Now that I've decided to shout all the time. And then up. And so here, what do? We start from S, and then we do the module F equals category F module G equals. Yeah, I keep forgetting it. Category G. And these should be private.
Yes, they should.
because otherwise I'm polluting everything. Okay, so what do? We transform a S into something of type M, and then we transform it into something of type T. And then for the morphisms, it's the same. We take our morphism, F, and we turn it into a home fun in T by turning it into a home fun in M first.
Home fun.
Oh, yeah. Oop. Autopilot.
Right, and then hopefully these actually just go away, right?
Oh, it's annoying, right?
And there's meant to be some fiddly yellow, isn't there?
Yes. Okay.
And that should be G dot identity. Yes.
It's
same thing here.
Same proof as always, right? You're doing 2 transformations in a row, so you need to push the structure through 2 layers. And here it's going to be the same. So FG, and I can rewrite the inner one, F and G.
Space after the, oh, you don't need space.
No, because they're modules, yeah. And then I can use this one.
Yeah.
And I'm doing this because then I get to solve the results, which are, of course, the transform things, because as you push them under.
All right, cool.
You're
2 minutes
transforming
to the
them.
hour, so we should not stand on ceremony, but
Yeah.
There we go.
But so you can see how you can now close the...
Guess what? It turns out that there's a category of categories where the morphisms are functors, because computer scientists love shoving things up themselves.